Tokenizing strings into words, sentences, and paragraphs is the first step in many common natural language processing tasks. While it may seem like a simple problem at first, string tokenization gets more complicated when you consider differences in how languages are written. For example, languages like Chinese, Japanese, Khmer, and Lao aren't written with spaces between words. Other languages have linguistic compounds that can be broken into two or more separate words, and it's often useful to split compounds into multiple tokens. And in Unicode, there is variation in punctuation characters used for different languages, which adds complexity when tokenizing into sentences. CFStringTokenizer solves these problems by providing a language-neutral tool for tokenizing strings. It also adds support for language identification and transliteration. So let's see how this works by tokenizing a simplified Chinese string into words. First, we set the string that we're going to tokenize. For those of you who are interested, this string is the opening of the Universal Declaration of Human Rights, which is useful for demonstration purposes since it's been translated into pretty much every spoken language in the world. You'll notice that there are no spaces between the words, and the full stop character is different from that used in the Latin script. Next, we create an array to hold the tokens, and then we're ready to create the tokenizer. We pass in the string we want to tokenize, specify the full length of the string for the range, and set the tokenization option to word. The function also requires a CF locale for region-specific tokenization behavior, and the documentation recommends that this be set to the user's current locale, unless the developer wants to specify a different locale. The next step is to iterate through the string and add the tokens to the array we created earlier. To do this, we use the CFStringTokenizer advance to next token function. The function takes the tokenizer we created as an argument and returns a CFStringTokenizer token type, which is an enum. If the tokenizer doesn't find a token, it will return none as the token type. So, while the next token is not none, meaning we have a valid token, we first get the range of the token with CFStringTokenizer getCurrentTokenRange. Then create a substring of our original string using that range, and finally add it to our array of tokens. After the loop has finished, we print the array to see the word tokens. With only a minor change, we can also transliterate the tokens by using the CFStringTokenizer copyCurrentToken attribute function in our while loop. We pass in the Latin transcription option, and then instead of adding the token string to our array, we add the transliteration string for each token. And you can see that the code now prints the Latin transliteration of the tokens. CFStringTokenizer also includes language identification support for a list of recognized languages. The list of supported languages is provided in the CFStringTokenizer documentation. To do this, we use the CFStringTokenizer copyBestStringLanguage function, which takes a string and a range. Here's an example using the same phrase from earlier, this time in Icelandic. We pass the string into the copyBestStringLanguage function and specify an empty range, which the documentation tells us will use the first few hundred characters of the string to identify the language. The output is IS, which is the language code for Icelandic. So that's CFStringTokenizer. There's another option for doing more advanced processing on tokens, such as part-of-speech tagging and named entity recognition. That's NS Linguistic Tagger, and it will be covered in a separate video.